Hey everyone, welcome back to my channel. In this video, we are going to learn an interesting data structure called UnionFind and cover which problem it solves and how it solves that problem. So let's imagine we have to group certain numbers. So meaning, let's say we have a graph that contains these elements and one is connected to 2 and 2 is connected to 3 and this 4 items are grouped like connected to each other. So let's say the parent of 2 is 1, so 1 is directly connected to 2, and parent of 3 is 2 and 3 is directly connected to 2. But that means 3 is indirectly connected to 1, and same applies to the second group. So and 8 and the third group. So 8 is directly connected to 9. And imagine we are going to connect this group to the first one. So meaning like if we connect any one of these elements to the first group, they will just union. So they will form a union, meaning like they're now in the same group. And this specific data structure called UnionFind does two operations. We have a function called union, so it accepts group A and group B, let's say, like any specific element of group A and group B, and it will just union them in constant time. And we have find method, so it will accept any element and it will also find the group ID for that element in constant time as well, like amortized constant, let's say, because it will operate some, it will need to execute some path compression to reach the parent, the root parent. So like here, the parent of 1 is 1, parent of 2 is 1, parent of 3 is 1, parent of, so this is the same like for all of this. This is called like we are effectively are compressing the path from root to leaf, like from child to root directly. For example, in order to find the parent of 7, we don't need to iterate through this path. We just directly go and access the parent in constant time, amortized constant. For this, we are going to use cache, and eventually it will find the result in constant time, amortized constant. So what's the point of this algorithm? So we can just find the parent of element 1 and find the parent of element 2, and we, by doing this, by checking this, we can check they're located in the same group in constant time. So this is quite useful data structure to have in your toolbox. So let's try to implement and test it with some cases. So we are going to define our class called UnionFind, and let's initialize our so it will accept And so this can be like modified based on the problem that you have. It can just initialize these number of elements that we have, or some other abstraction can be applied here, but eventually it will just create parents dictionary, parents, and this is a dictionary. So we need to, so at first, let's say we are keeping track of parents, right? So we have like, let's say 4, and the parents we are keeping track are same as the element. So meaning like parent of 4, element 4 is 4, parent of element 3 is 3, parent of element 2 is 2, and parent of element 1 is 1. So they're not connected. Like this is our parents. If we update the parent of 2 to be 1, so now this 1 and 2 are directly connected to each other. So this means, this indicates that they are located in the same group, and we can leverage it when we are uh, connecting items and when we are trying to find group of certain item. So because of this, we are going to initialize uh, element now. So let's say for I in range, and let's say we are generating n slots for our UnionFind. So and the parent will be I, and the child will be itself, meaning its parent is its own itself. And we are going to define our function called union, and let's say it will accept a and b. These are the numbers, and let's assume they're always on this dictionary. We are going to implement this, and we are going to implement our find self.a, and it will return integer, and that integer will be the parent. So let's say we're going to union this to, let's say this case, this is 2 and a and b. So where a is 1, b is 2. We need to find the root of both a and b. So how do we do it? So we are going to call this find function, so it will accept a and root a and root b self.find b, and then we now have roots, like root parent of both elements, and now we can just say that self.parents root a is equal to root b. So the parent of a here is now b. Let's say if we call union function with a being 1, b being 2, so parent will be the second one. So parent of 1 now 2. So it doesn't matter as of now. Like we can certainly optimize this function by including sizes, and like then what we can do is, like, let's imagine we have this group and this second group, and if we want to merge these two groups, it will be more easier and require less operations if we merge this to the bigger one. So in this case, we will need to just need to update our caches uh, less times. For example, here we have 7 elements and here we have 2 elements, and as this find operation is amortized constant, that means we need to um, update like this parents dictionary 7 times for each element. And to reduce this, we can introduce sizes um, dictionary. So this means, like, let's say we have initially the size of 1 for each element in our UnionFind, so it will be I will have size of 1, and for I in range n. So it makes sense, right? So now we have size, and we can check the size of this if self.sizes of root A is smaller than self.sizes root B, then we need to merge A to B. Okay, this makes sense. And then we can just early return, so we have done this operation. If they're equal or the root of B element is bigger, then we can do the reverse here. And this is it for our union function. Now we need to implement find. So in order to find, we need to recursively try to reach our parent. So how do we do it? Let's say in this case, we haven't optimized or cached our result yet, and we need to, let's say this are not merged yet. Now we need to merge. So the parent of 7 is 7, meaning it's not connected to anything. And so this means like if self.parents A is equal to A, then we can return A itself, right? Else, what we can return is self.find parent of A, as they're not equal. And this is it for our find method. And most of the time, it will hit this cache, meaning it will return the result in constant time, and sometimes it will just um, recalculate parents and set parents. So we need to do some other thing here. So we need to set. So the self.parent, because we are just doing caching in here as well. So, and eventually we can return this. And also we need to update sizes. So self.sizes root B plus 1, and here we will update size of A, and then we're done. Now what we can do is we can initialize UF equals union find. Let's imagine we have 10 elements, and now they're not connected. So let's UF dot union, let's connect 1 and 2, 2 to 3, 4 to 5, and 4 to 6. And we can now check, we have formed a group. So let's check print uf.find, let's say find a group of 1, and uf.find a group of 6, and it will print true if they are connected, false otherwise. In this case it will return false. So Python 3 UnionFind, so it will return false now. So if we connect them, let's connect 1 to 6, and now this time it will return true. So this is effectively it for the implementation of this data structure, and you can play with it, we can modify it, you can apply it in the problems that you face. So you can also introduce add method here, and it will add certain elements to the parents table, and then you can just modify and apply it in depending on the problem that you have, and keep learning. Thanks for watching. Bye bye.